So this is just, in your notes, I think this lesson is just called graph examples. You know, and I called it on the board there, I called it Intro to Rate of Change, Part 2, basically. It's also part of that same lesson. And again, short homework, but very thoughtful homework. You really have to think about what's going on. Well, turning displacement time graphs into velocity time graphs is extremely difficult. It sometimes takes 2 or 3 times through this before it really starts to make any sense. So what I'm going to do the first time through is try and show you some very specific techniques to handle the situation until you get a little bit better at them. Like step 1, do this, step 2, do this, and so on. There's good news. If the displacement time graph is a straight line, so I'm going to add that to your notes right away. It's just say, hey, we're talking about a straight line here. I'm unhappy with the thickness of my pen here. If it's a straight line, find the slope. And I'll talk more about what that means in just a second. But when you have a straight line on the displacement time graph, first find that slope, and then I'll tell you what to do with that slope, okay? Now, finding the slope, what's interesting about finding slopes is, back in grade 9 when we first taught slope, we said, hey, you can use any 2 points in the line. And the reason you can use any 2 points in the line is the slope of this is the same all the way along the line. The slope from here to here is the same as from here to here, from here to here. Any 2 points will do. So you got your choice of points. Now, if you get a graph that doesn't give you really, really nice points and you have to estimate, your answer might be slightly off. And that happens with graphs from time to time, that your answer is slightly off. This one, I tried to draw it on your page so that you can see very specifically what the points are. And I'm going to grab 2 very far away points and then talk about what would happen if someone used 2 much closer points, okay? So I'm going to grab this initial point. This thing apparently has displacement 10 meters at time 0, and I'm going to go way over here and grab this point here. Many, many choices available, all which will give the same answer. They will give the same answer up to rounding, I'll say. It can be, sometimes you have to estimate the points, and it can be slightly off. So don't get too carried away if your answer is slightly off. Anyhow, way back in grade 9, you had several ways to handle this situation. One of which was just to go, okay, let me just actually find out what the rise and run are. And so if I just look at this, if it starts at 10 and goes up to 80, it has rise 70. If it starts at 0 and goes out to 14, it has run 14. So the slope is 70 over 14. Now, if your brain's screaming at you going, yeah, wait a minute, what happened to y2 minus y1 over x2 minus x1? Wasn't that the way we were doing slopes in grade 9 and 10? Absolutely. We're coming right back to that. Like, that is like one lesson away. Tomorrow afternoon, I'm right back with y2 minus y1 over x2 minus x1. But I don't want to get distracted by that. Just right here, I just want to go, listen, you just got to find the slope. If you're a y2 minus y1 person, you remember all that? Absolutely, that perfectly works. I just want to focus on rise over run here. 70 over 14, which I get, when I reduce that, I get an answer of 5, the number 5. Usually with velocity, we can go with decimals. In grade 9, we kept them as fractions usually because we were doing graphing with y equals mx plus b, so we like the fraction there. Here it doesn't matter. It's not even a decimal, so 5 is perfectly fine here. Somebody else goes, well, no, what if I use 2 different points? What if I happen to use those 2 points? And if you did, you would have got slope 20 over 4, and 20 divided by 4 is also 5. So it doesn't matter which 2 points you choose, you'll get the same answer. Unless you have to estimate points, and then you might get, like, somebody else might have used 2 slightly different points, and they might have got 5.1 or something like that. It's the best we can do off graphs, is get a good estimate. So, hey, listen, I started this by saying, for a displacement time graph with straight line, find the slope, okay? So, now here's my sales pitch on what we have to do over here. That means that whatever we're talking about here, every point on the line, whether it was at time 0, time 2, time 4, all the way through, this thing had the same velocity. It had velocity 5, it had velocity 5, it had velocity 5, all the way through velocity 5. That's the nice thing about straight line graphs. They have the same velocity all the way through. So let me go over here and graph the velocity at any particular time. At time 0, it had, oops, oh, I need some, a scale here. 1, 2, 3, 4, 5. I get to choose my scale there. And at time 0, it had velocity 5. At time 2, it had velocity 5. At time 4, velocity 5. It's always velocity 5 up until right when it leaves the graph here at 18. So I'll stop at 18, even though it really looks like it just keeps going on. But there's no arrow there, so I'll just stop. They stopped at 18. I'll stop at 18. And so what you get here is just a straight across horizontal line at 5. Now, I went through the individual steps there of putting dots all the way along, only to explain the thing to you. You might just go, okay, once I've got this 5 here, I know that what the velocity is always going to be. It's always going to be 5, and you might just draw your straight line just across. Yeah, so here's my steps. If this is like, oh, I don't really get velocity physics, it's not my thing. Okay, here's the steps. The steps are straight line, find the slope, and on your velocity time graph, draw a horizontal line. At the value of the slope you found. So this comes up with a catchphrase. Straight line displacement time graphs result in horizontal velocity time graphs, because both show the same thing, although it's hard. It's hard to switch your brain between displacement time graphs and velocity time graphs. In fact, when I talk to calculus people, the ones who take physics, they go, I'm finally good at it. Yes? I saw it in advanced functions, I did it in physics, and now that I'm back in calculus, I finally feel like I'm really good at it. Till then, stick with the procedures that I give you of how to do these until it really, really makes sense. So if you're looking at this going, I only sort of get what's happening here, that's about where most people are when they first see this. But let me explain it once more. So maybe, just maybe you go, oh, I get that. What's he talking about? I totally get that. This graph shows, by going in a straight line like this, it shows that the velocity is always 5 on the displacement time graph. To show that the velocity is also always 5 on the velocity time graph, I just have to stay at 5 the whole time. They're showing two different things, but they're showing the same information. Yes, so this graph is showing we're going up by 5 kilometers every hour, but because this graph's a velocity graph, it's showing 5 kilometers an hour all the way across. They're really showing the same thing. There's like this moment when you're looking at them going, oh, it's the same information, just represented in a different way. If you want, this is a slope time graph showing what is the slope at every particular time. So you go, okay, what's the slope at time 2? Oh, the slope is 5. Okay, slope's 5. What's the slope at time 4? Oh, the slope's 5. The slope's always 5. And you go, slope's the same as velocity? Yeah. There's the big idea right there. I wrote it on my poster back there. Slope means the same as rate and speed. You're like, you said speed and velocity were different. Well, yeah, there was negatives available here. We could get negative velocities here. What would this line look like? What would the only difference be if it was negative velocity instead of positive velocity? Yeah, just give it a thought for a second here. Back in grade 9, this was called positive slope. How do you get negative slope? Just by going downwards, eh? So then if I had gone downwards, I would have got negative slope, and my answers would have been down here. Okay? If that is like, I sort of get it, my very next example is I'm going to do that 3 more times. So if you sort of got it, I'm going to go through the whole thing again 3 more times, and then we'll pause and go, does it make sense? And then looming in our future is, what do we do if it's curved? Yeah? And then that's a whole nother strategy. Well, it's not a whole nother strategy. I've got to add on to my strategy. Okay. So from the previous page, it said, if you have a straight line graph and you want to make the velocity time graph, find the slopes. Okay? So the slope of this one, I got to find 2 nice points here. I think 0, 7 is a nice point that it goes through. And then I think this one here is a really friendly point, 4, 0. Your job, find 2 friendly points. If you're really suspicious about this, you're like, well, what happens if I don't select the same points that you did? You'll get a very close answer. Like, instead of I got 5 in the last one, you might get 5.1 or 5.2 or something like that. And I'm going to go, yeah, that's fine. Because graphing isn't like a perfect procedure. Algebra is a perfect procedure. You get perfect answers. Graphs are always sort of an estimate, you know? Anyways, I'm not going to do the y2 minus y1 over x2 minus x1 thing. I'm going to do lots of that tomorrow. So that's not gone. I'm just trying to make these examples really simple so you see what's going on. So, mistake coming. Yeah, mistake coming. Get ready for it. If when I write stuff here, you're like, wait a minute, something's wrong. Get ready. I'm going to ask that. So this is rise 7, run 4. So the slope in that part is 7 over 4. I better get it as a decimal if I want to graph it 1.75. I'll give you some time to think about the mistake I've made. You can write most of that down because the mistake's easy to fix. This one here. Well, I don't need y2 minus y1 over x2 minus x1. I don't need rise over run. I shouldn't need anything to figure out the slope of a horizontal piece. How much is this going up by? That's what slope is. How much is it going up by? How much is this line going up by? 0. It's not going up by anything. So if that's not in your bag of tricks yet, please add that to your bag of tricks, which is a horizontal line has slope 0. We won't even talk about vertical lines, right? Because vertical lines have no way to describe their slope, but we don't need that right now. We'll just leave that on the shelf. Then it says find the slope of this next part. I think there's 2 good points there. And again, don't freak out if you choose different points than me and get a slightly different answer. That's no problem. And so I get rise 1, 2, 3, 4, 5, 6, 7, 8. Run 3. So this slope is 8 over 3, which is about 2.7 when I round it, okay? And just to be a little bit official, math-wise, maybe I should go, oh, this is slope 1, this is slope 2, and this is slope 3. Although I'm not winding up to get wound up about those little things. I'd be able to follow what you're doing here. I just mentioned that's really formally what we should write there. Did anyone catch the very tiny, except extremely important, mistake I made here? Yeah, this one's negative. It's going downwards, or the displacement's getting smaller, or it's getting more negative. All of those things are true, but whichever one makes the most sense to you to go, oh, that would be negative. It matches up with slope, right? The slope here is negative because it's going down left to right. So, as weird as this is, I've just got to graph these 2 slopes. And let me go through the procedure again. The idea here is that everywhere on this line, the slope is the same. No matter where you go, that velocity, yes, slid that word in there. I'm trying to interchange between slope and velocity where you go, oh, slope and velocity, same thing. Everywhere you go, same slope. Like at every point here, the velocity is the exact same. What is that velocity every single time? Negative 1.75. So I'm going to go graph that over here. I'm going to use a weird scale here to try and make it a little more easy to see what I'm up to. Is this going to be big enough? No, that's too small. Okay, so it's got to be every second one. All right, just a second. 1, 2, 3, 1, 2, 3. That should be enough. And I'll do the other points in blue so you can really see them. And if you're sort of lost, here, let me go and explain the whole thing again. Everywhere from this time all the way to 8 and a bit seconds there, what's the slope every single time? What's the velocity every single time? Negative 1.75. So what I get here is it's negative 1.75. It's negative 1.75. It's always negative 1.75 all the way up to this point of, what, 8.5, somewhere in there. See how I'm just sort of guessing. I'm just sort of estimating about where that thing ends, and that's okay on graphs. Somebody else goes, no, I totally get this. I don't need all your little dots to think it through. I'm just like, straight line, always equal to negative 1.75. Then, next section, between 8 point whatever and all the way over to 13, that velocity is always 0. So let me do it the easy way, which is to go, okay, between there and there, it's 0. Every single time I check the velocity, it's going to be 0 velocity. And so I get a straight line in there, across. Let me go back to the previous slides and see if that's what I said in the previous slide. Straight line, find the slope, then draw a horizontal line at the value of the slope you found. Last slope was 2.7. Maybe you're getting a little better at this point where you just go up there and you go 2.7, whoop, 2.7 right about there, all the way up to time. It looks like it ends at 19. Maybe it's supposed to be an arrow and continue on, but you know, that's not really what we're worried about, particularly on these examples. One last physics thing, and then I'll pause for questions. This graph is not perfectly realistic in the sense that you can immediately change your velocity from negative 1.75 and jump to velocity 0. That's not realistic. The only way I could really do that is if I just ran towards that wall at full speed. Wouldn't it be great if I just demoed that right now? Wouldn't you crack up? Just imagine me running into that wall and knocking myself out on the floor just to make the point. Yeah? Well, to make a lot of points, actually. Okay. So to instantaneously change velocity, I'd have to be running like that and then clunk. For you physics people out there, actually, that's not even instantaneously stopping. There would be, you ever seen a picture of a golf ball being hit? I sometimes put it on the internet and so on, where the golf ball's like completely like misshapen. It's got like it's like a circle, but it's got this big side to it. Even if I ran into this wall, I wouldn't stop instantaneously. There's to be this moment where my nose made contact, and then it would shrink down and go like that. There'd be this very small time frame where I'd slow down. So these jumps in the graph here, these instantaneous jumps, aren't very realistic. What should we really have? And I'm not warming up to make you do this. We don't make you do this till calculus, but you really should have nice smooth curves here and a nice curve here, something like that. But that's not really part of this course. But I mention it because it's a little unrealistic what I've drawn here. Okay? Now I pause for questions. Any questions about straight line displacement time graphs and finding the corresponding velocities? What's that? Yeah, it's not clear exactly when that happens. So technically speaking, you're right. We either have to have open circles, closed circles, or a curve. Something's got to happen to really make this really match up with what happens here. We'll leave that to the physics people. Yeah? For our purposes, this will be good enough for what we're working on here. So I'm not going to get too excited about what you do with those junctures just yet, because there's a lot going on there technically. If we really want to get technical about it, there's a lot going on. When things collide, a lot of stuff happens that we'd really have to talk about. 2 chapters of physics I think it would take before we go, okay, now I understand collisions, now I'm ready to actually do this graph perfectly. Yeah? That's not our job right now. I did that curve to say, technically speaking, it's probably the situation where there's going to be this time when you're slowing down. You can't just instantaneously stop and jump from one velocity to the other. Yeah, it's got to be smooth somehow. I'm not asking you to do that. If you guys draw this, and you don't have that curve down there, I'm like, yep, yeah, that's fine for our course. We're just getting the idea of, we're mathematically trying to find these different slopes. We're trying to do what that says to do, which is, and with the corner there, that's what it's saying to do. Apparently, they instantaneously changed velocity. The example I always used to use, and I did earlier today, was the train example, because that was the best way I could illustrate what this graph is showing, is that if you want to go right from positive velocity to negative velocity, you got to get hit by a train or a car or something. That's the only way to instantaneously change from one to the other. But again, these are all physics conversations, not really what I'm trying to get to in the math. Other questions there? Okay. Curves. Curves are a big problem. And I'm going to try and give you some strategies to handle what to do in curving areas. So the first strategy I'm going to do is say, is there a velocity that we can find in here? Because it's not easy. If I were to put a ruler on there and say, what's the velocity at most of these times, It wouldn't be easy to do. Anybody who's going on to physics, this is exactly what you'll do. You'll take a ruler like that, you'll draw a line, and you'll find its slope, and you'll do it at all sorts of different times. Okay? You can't, that works. You can do that. But is there any times you can look at and go, oh, I know what the slope would be right there? Yeah, these two are key points. Right there and right there, we do know what the velocity would have to be. And if you really haven't spent much time thinking about physics, let me just throw something in the air and talk about it for a second. If I take a piece of chalk and throw it straight in the air and it comes back down again, on the way up we could say it has positive velocity. On the way down it's got negative velocity. And the only way to get from positive to negative, there's a number in between that you have to go through if you're going to go from positive velocity to negative velocity, and that number is 0. And that conceptually is a little bit difficult to go, oh, this piece of chalk must stop at the top and then come back down. That's impossible to see, right? Even with slow motion, you would never see it stop, but that's what has to happen if it's going to go from going that way up to going that way down. At some point, it's going to have to hit 0. Graphically, if I were to draw, I'm moving ahead, and this thing's called a tangent line. We're only one lesson away from learning, or 2 lessons away from learning about tangent lines. But if I were to draw a line to represent the slope there, do you see how it would be horizontal? And horizontal there, if I was to do a line there? And it's a little hard to visualize right now, and there's lots of talk about that coming in the next couple of lessons. But if I were to do that right there and there, m equals 0. And right there, m equals 0. That's shockingly helpful. It seems like not much information, but it's unbelievably helpful, because then I can go and say, okay, at time 3.5, it looks like, I know the velocity must be 0. And I know another 0. At time, 12.5, right around there, it must be velocity 0. And that does an unbelievable amount of help for drawing the velocity graph, because I know 2 of the zeros. Let's talk about what could happen. You have a little experience of this from last chapter where it said, I gave you 2 points, and then we talked about it's got to be increasing between this point and decreasing, all that stuff. There's only a couple possibilities here. This graph either sort of goes down through the first point and then comes back up, sort of parabola-like, or it goes this way. Those are the only 2 real possibilities if those are the 2 zeros of what's going on. So, then it comes to this. The question is, should I go positive velocity and be up here, down to negative velocity, and back up to positive velocity? Or should I go negative, positive, negative? I mean, that's the big question is what are the signs going to do? So let's just talk about that. In this section right here, is the slope, or the velocity, is it going to be positive, or is it going to be negative? Well, let's just talk about right here. Right in that section here, is the displacement getting larger or smaller? It's getting larger as it goes into there, yeah? It's going up. So this is m, and I'm just going to put a positive sign there. We must be positive slope in there. Between here and here, are we positive or negative? We're going back down again, so this must be negative slope. And then this one, at the end here, back going up, it's m positive. That's enough to get the graph. I can get the graph from that information. I want to do a little bit better than that. I'm going to just do just a little tiny bit better than that. Take a look at this slope as it heads into here, and this is a huge calculus type idea that's not that complicated actually. It's one of the big things we do in calculus, except it's not that complicated. As we go into this maximum, what's the slope heading towards? It's got to head towards 0. So I've got a positive slope that's got to head towards 0. So I've got to start with positive values and head towards 0. You're like, you don't know the specific values there, Mr. Todd. I don't know how you're coming up with this. No, I don't. I only know the shape. So in advanced functions, we only want the shape of the velocity time graph. Shape will do. Shape is good enough for us. And again, we leave the next step to the physics and the calculus people to get these perfect values. Has anyone signed up to take physics this year? A couple of people. So some of these things you'll go the next step in physics later, and then you'll go the next step with me in calculus later. Oh, or well, it doesn't have to be with me. It depends on when you take it, who you'll get. Okay, big moment here. This is the section that some people's eyes go from this, frowning at me like, are you kidding me? To going, oh, I got you. We're okay. So stick with me for just a couple more minutes. Let's take we'll call this a slope calculator. Just imagine that this had a little digital display on it, and the display would come up with the slope. I had just hold it up like that and we go, oh, slope 5. Oh, slope -2. Like a little level. Let's talk about what happens to the slope as we go from here, this point here, at t equals 3 to t equals 13. Starts at 0, yes? Then it starts to go negative. It's going negative, negative. Then it starts to level out. Still negative, but it's coming back. It's coming back. It's coming back. It's coming back. And heads towards 0. We say that in words. Start with 0. Get negative for a while. Then head back towards 0. We say that out loud while I draw the other graph. Start at 0. Go negative for a while. Then come back to 0. Smaller. This is a smaller version. It's a... Yeah, I guess I don't really know how low it's going to go. I'd have to do some calculations to figure out how low it's going to go. Again, the shape is the best we're going to do here. To get the specific values, I can get these specific values, but I either need physics or I need calculus to get specific values. Right now, I can just talk about the idea. If that's sort of caught in your brain, it happens to me all the time, I don't know if it happens to you, or an idea sort of goes through my brain, and for a moment I'm like, oh, I kind of get it, and then it just slides away on me. Maybe it's an age thing, but maybe it happens to you too, where it's like, oh, I see what he's saying, no, I don't know what he's talking about. You know what I mean? Let me try it again for this last section in here, okay? We're just talking about the slopes. The slope in this section starts at 0, and then as it goes this way, it starts to get positive. And then it gets more positive. And then it gets more positive, and then it gets more positive. It's getting really positive. It's getting bigger and bigger positive numbers. So when I go to graph here, I start at 0, and I'm getting more positive, more positive, more positive. Oh, there's no arrows on this thing, so I'm not going to put the arrow on there, but something like that. These are extremely difficult. Why does that help you? I mean, for some people that doesn't help them. Like, oh, great. Even the math teacher is telling me they're difficult. No. That means you don't have to be too hard on yourself. You don't have to be doing these questions and going, oh, I'm so stupid, I can't get these. No. These are hard. And I've kept it down to 2 cases. One case, straight lines. Second case, curving. It really helps to think, where's my, see all these little notes I've made on here? That really helps. Question. They could be. They might be. We don't really know for sure if they're going to be straight or not. So if somebody on the test for this, and I'll draw it in red, okay? If somebody on the test for this went, oh, and did that, I'd be like, yeah, okay, yeah, shape. Is that what you meant by straight? No, then tell me what you meant. I'm a physics dude, by the way. My degree technically is more in physics than in math, or it's about equally split. So I'm easily distracted by physics. So go ahead, tell me. These ones? Yeah. He's right. I don't know for sure, based on this curve, whether this thing is just going, the velocity is getting bigger at the same rate or not, that its acceleration is constant. I don't know that for sure. Yeah, is to know whether that is what's really happening there. Without the equation, I'm rooked. I don't really know for sure. Now, I will tell you, that as you learn more about these things, as we go along, and it's about halfway through the calculus course, that you'll start going, hey, when it does this, this is sort of like a, what do I want to say to use the right words here? This is smooth, so this will probably be smooth. The actual equations of these things that I've stolen these from actually makes it that this is what happens. So I start to do that to get used to it. At the same time, I won't argue with straight lines at all. The zeros and the right shape is all we really are trying to accomplish in all this, yeah? Going in the right direction, yeah? Other questions? These take a little practice, and that's why the homework is whacked, yeah? It's like 4 or 5 questions of like sitting there staring at it going, So instead of, the homework I've given you so far can cramp up your hand where you're doing pages and pages of writing and graphing. This is more like sitting there with your fingers dug into your temple going, what's going on here? Okay, there's the answer. You know what I mean? Like it switches over for a little while here. If you don't like that, well, that's okay, because starting tomorrow, it's cramp your hand time again when we get back to the next section. So this has a little bit of each.